that's crucial for the next assignment. Boys, we're still missing half the class. Maybe Dawn extended the time.
Not according to chat.
No, okay. So maybe people are recuperating. So we're going to start it up. We're looking at chapter 9, and there is a test coming up. Test number 3 is going to be chapters 8 and 9. And these chapters are all about being able to solve circuits that are not series and not parallel. So we need some special tools, and the author of the textbook decided to split those tools up. There's a lot of them, and we're going to focus on only 2 of them in chapter 9. So basically that's what I just said here. So the 2 we're going to focus on in chapter 9 are superposition and Thevenin's. Superposition is sometimes one of the easiest methods. It basically deals with, especially if there's only 2 sources, it deals with removing one source and solving the circuit, then doing the same by removing the other source and solving the circuit and adding the results, basically summing the results. One limitation of superposition, it's only useful in circuits with multiple sources. So if you only have one battery, one power supply, superposition is of no use to you. It's only good with multiple sources. And then the second one we're going to look at is Thevenin's. It's applicable for almost any scenario. You can use it anytime, though there are some cases where doing a Thevenin circuit might not necessarily reduce the circuit or make it easier. Thevenin is great in that it says that any circuit in the world can be represented like this, where we have a Thevenin voltage source and a Thevenin resistance. So that's Thevenin's premise, is that the most complicated circuit in the world, anything, can be represented like this, as long as you do it properly. It's useful in solving complicated circuits. It's useful in circuits, we'll see in the assignment, if you have a load which varies all the time. And that's a real life scenario where you're changing what the resistance of the load is. Well, if you use nodal, mesh, superposition, any other calculation, you have to redo it all over again when the load changes. With Thevenin, you don't. You do Thevenin once, and you've got this equivalent circuit, and it makes recalculating everything with a changing load a lot easier. That's one of its claims to fame. It's useful. It's one of the ones that we'll use later for sure. If you're trying to match your circuit, if it's an audio amp and you're trying to match it to your speaker or your electric guitar or some transmitter, you have to look at the Thevenin equivalent circuit. If you're hooking up antennas, you have to look at the Thevenin circuit. Even when looking at hooking something up to your cell phone, you can't hook up the same speakers that are on your big stereo to a cell phone. Headphones is what you're going to hook up to your cell phone, and the headphone impedance matches your cell phone. The 8-ohm speakers do not. Never try and hook up 8-ohm speakers to your cell phone. And it all has to do with matching, making sure it's appropriate. And Thevenin brings us there. We're going to touch upon maximum power transfer, and we'll find that maximum power is transferred when the load is equal to the Thevenin resistance. And later on in electronics, we will look at frequency response, important in audio, in antennas, in everything. And Thevenin is also very important. And I'll end off this little summary of Thevenin saying that Mr. Thevenin looks into the circuit from the point of view of a couple of terminals that we put in there. So if you want this to occur, what you basically do is you remove the load and you look into the circuit and determine what you see. And that's why it's important for audio, for speakers, for antennas, for anything where you have to look in and match what you're seeing in there. So that's Thevenin. I feel that Thevenin is the one that you're going to see the most often later on next year, and maybe even 5 years from now, 10 years from now. Let's mute some microphones here. So again, we're looking at two new tools, superposition and Thevenin. Starting with superposition, we need a little bit of background information before we can use superposition. We're going to introduce that here. So superposition just means that if you have multiple sources, if you have two batteries, solve the circuit with one, solve the circuit with the other, add the results. If you have three batteries, solve the circuit with the first one, solve the circuit with only the second one, solve the circuit with only the third one, add the three results. So you'll have to analyze it as many times as you have sources in the circuit and just add the results. Whoops. But to do that, we need two important rules. The two sources that we've learned to deal with right now are, that's what we're going to use most of the time, is the voltage source, battery or power supply, but we've also introduced the current source right here. So these are the two sources that we're going to use, and just note that if you are using superposition to solve a circuit and you have two batteries, so you have to do it twice. The first time you do it, when you remove the second battery, you must replace it with a short. So if one is to remove a battery here, we replace it with a short. And when you come to the lab in January, we'll see that's the case. Whenever you turn the power off, if this happened to be a power supply plugged into the wall, producing so it's a DC power supply, and you've set it to whatever, 12 volts. When you turn off the power, it acts like a short. That's what DC supplies, that's what even batteries, that they are to be replaced with a short when we turn them off or temporarily remove them. On the other hand, current sources, when we turn off a current source, it's replaced with an open. So current sources are to be replaced with open circuits. So we have to remember that. Most of the time we're dealing with batteries, so make sure so we're going to see what that means here. Actually, we're going to do an example that's got one of each. So superposition, if we want to use it, we could use nodal, mesh currents, loop currents. We could convert the voltage source with a series resistor to a current source with a parallel resistor. So we have all kinds of tools. We're now looking at one new tool, just what you need, another tool. And superposition says we've got two sources, two sources. So we're going to analyze this twice. We're going to analyze it once with only the voltage source. We're going to analyze it a second time with only the current source, and we'll add the results. We'll be done. So first, we're going to turn off the current source. So we're going to remove the current source here, and current sources must be replaced by an open. So all we're going to do is remove it and solve the circuit. So when we solve the circuit, I think all we're left with is a simple series circuit, and we have I as 36 volts, the applied voltage, divided by 12 plus 6, 18 ohms. And so we end up with 2 amps. It's a simple series circuit, so there's 2 amps flowing everywhere in the circuit. There's an open here, so this is 0. This is an open circuit, 0. We do have 2 amps here, 2 amps here. Now what you might notice right away, we won't even mention that. Okay, what's going to be critical here, step 1, we're going to remove the current source. Step 2, we're going to remove the voltage source. So what stays the same, that never changes, is R2. So this will be important here, that we have 2 amps flowing down through the 6 ohm resistor. That was step 1. Step 2, we're going to turn off the voltage source. When you turn off a voltage source, you replace it by a short, and we're left with this circuit. What you have to be able to notice in this circuit is that, yes, that the 6 ohm and the 12 ohm are in parallel. We can slide that 12 ohm over here. The right side of the 12 ohm and the top of the 6 ohm are connected together. The left side of the 12 and the bottom of the 6 are connected together. That by definition is parallel, and we have 12 in parallel with 6, giving us, had that done, but I don't remember it now. 6 12s are 72, divided by 18, 4. Okay, come on, tablet. 4 ohms. So what we really have here, if we wanted to simplify this a little bit, 9 amps and 4 ohms. That's our equivalent in this temporary circuit. 9 4 ohms, so we can pick that out. 9 times 4 is 36 volts. So 36 volts from this point to this point. So 36 volts. So in this circuit, we actually have 36 volts across the 12 ohm, giving us 3 amps, and we have 36 volts. It's a parallel circuit. It's all the same voltage. 36 volts divided by 6 ohms, giving us 6 amps. That means this total I must be 9 amps. But circuit number 1 and circuit number 2 are not real circuits. They're temporary circuits in the steps of solving the real circuit. In these temporary circuits, the only thing that did not change is R2. It's still right here between those terminals. And in this first circuit, we determine that 2 amps is flowing through R2, contributed by E. In the second circuit, we see that 6 amps are flowing through the 6 ohm, contributed by current source. So the 2 amps and the 6 amps, they're actually in agreement. It looks like we're pushing current in the same direction, and they agree, and they add up, and what they add up to is 8 amps. So in the original, the real circuit, we're going to have 8 amps flowing. Nine amps. So if 9 amps flows in, we got 8 coming down. 8 amps through a 6 ohm resistor means that the voltage across the 6 ohm resistor must be 48 volts. So over here, across, we have 48 volts across the 6 ohm resistor. 8 6s are 48. Zero. Go up 48. 48 volts. Go up 36. 36 volts. The drop across R1, we're going from 48 to 36. The 48 is the more positive. And so that's a drop of, looks like 12 volts. 12 volts divided by 12 ohms tells us this is 1 amp. It looks like we are charging the 36 volt battery. We have 1 amp. 1 amp. Current source fixes this at 9 amps. And so this must be 8. 1 plus 8 gives you 9. So we better check. Yeah, it all works out. Kirchhoff's current law, KCL, says these have to add up. KVL says if you go up 36, and then we're going up 12, we get to 48, and then we can drop 48, and we're back down to 0. Looks like everything's checking out here. So the trick here was to find the contribution from one, the contribution from the other, and add them together. The other trick, we saw that the 6 and the 12 were in parallel. And another thing that's hard on the head is we determined that 2 amps was flowing from E, yet here we have 1 amp flowing into E, which is correct. This is the real circuit. These are not. They are temporary tools, temporary circuits in the steps to give us some information that we can bring back to the real circuit. So don't be bothered by these temporary currents and voltages. We must throw them away once we've extracted the information we need. The information we need or want, it's usually a resistor. I'll try and call it RL in some of the tests, but it's the one that's not changing. You know, it's the one that's not affected by turning off powers, turning off voltage sources or current sources. Any questions so far? So this is new, a new concept. Voltage sources are replaced by shorts. Current sources are replaced by opens in temporary circuits that we're using to extract information. Let's try another one. Yeah, that's just saying what I did. So you'll notice there's a revised PowerPoint for Chapter 9, and it'll step you through it. If you run the PowerPoint, you can step through what I've done here. So we're going to look at a second example here. This time we have two voltage sources. One might be tempted to convert the voltage source in series with a resistor. We could convert both of them to current sources with parallel resistors. We'd end up with an easy circuit to solve. If I had this on a test, that's probably what I would do. I would use voltage source to current source conversion. We could also use nodal analysis, looking at currents entering and leaving nodes. I see this one heading down here, so I'd probably show this current this way, this one this way. This one I'm not sure. I suspect the 54 might be pushing harder, but it's got a big resistor there, so I don't know. I'll show this down. If I end up with a negative answer, it means it's actually going up. So I could use nodal, but this is superposition. We're going to use superposition. Step 1, turn off one of the voltage sources and solve the circuit. So I turned off the 48 volt one, and that left me with 12 in parallel with 4 over here, which is actually 3 ohms. And that's in series at 24. So I can easily find some stuff here. I can find this current as 54 volts divided by 27 ohms. 27 is the 24 plus the 3 equivalent. Once I do that, I can find this current, subtract the volt drop from 54, giving me this voltage, divided by 12 ohms, and we'll end up with this current. 54 divided by 27 ohms happens to give you 2 amps. And when you multiply 2 amps by 24 ohms, you get 48 volt drop. So if this is 54 volts and I drop 48, then this must be 6 volts. And so if we have 6 volts dropped across 12 ohms, we've got 0.5 amps. 0.45 amps. Now the reason I zoomed in on the 12 ohm is I know that when I turn off this battery, it affects this branch. When I turn off this battery, it affects this branch, but I am maintaining this branch. So maybe I'll call that RL. It's already called R2. I'm going to keep that information. So I see here that there's 0.5 amps contributed by the left battery. It's kind of contributing 0.5 amps down. Next, I'm going to turn off E1 and replace it with a short. That's step 2. And when I do that, I'll see my 12 is now in parallel with my 24 here. And the 12 in parallel with 24 is 8 ohms. So then my current here can be found as 48 volts divided by, what's that, 4 plus 8, 12 ohms. We've got 4 amps. 4 amps. 4 times 4 is 16. So there's a 16 volt drop here. Uh-oh. Doing this all wrong. How do I undo this? Well, we'll use my eraser. What did I do wrong?
Excuse me, sir.
Amitage?
Yes, sir. Sir, the circuit over where we have short circuited the 48-volt battery, and in the solution, can you explain the 54/27 is equal to 2A?
Yes. Yes. What we saw that the 12 ohm and 4 ohm in parallel
Okay.
gave
We have
us
just
3 ohms. And now
okay.
this 3 ohms is in series with the 24, so that gives you 27.
Okay, we just have solved all the circuit and okay. Thank you, sir. Simplified the circuit. Yeah.
Okay. So what mistake did I just make here? Current leaves the positive of a battery. This battery is upside down. So current's heading this way. It's still 4 amps, but it's heading this way. 4 amps. It's going this way. 4 amps. The 4 amps splits in 2, and it carries on here. I don't know what these 2 currents are that it's split into, but I know 4 amps is entering, and when it recombines, it becomes 4 amps again. So the 4 amps times 4 ohms giving us a 16-volt drop is this way. Current enters the plus and leaves the minus of resistors, but it must leave the plus of voltage sources. So the 16-volt drop is this way. But when I look at my 0 here, this is a 48-volt drop. So over here must be minus 48 volts. Then I have a 16-volt rise. Minus 48 plus 16 gives us a voltage here of minus 32. This is still 0 volts. So the drop across a 12 ohm resistor must be 32 volts. 32 divided by 12, that tells me that this is 3 amps. And since 4 enter, 3 leaves, this must be 1 amp. Uh-oh. Where's my mistake here? 32 divided by 12 is not 3. What's 32 divided by 12? Nobody's helping me.
8/3.
2.67.
Yeah.
2.67. 2.67 amps. That means this must be 1.33 amps. And 1.33 amps multiplied by 24 ohms gives you 32 volts. Better. 2.67 amps times 12 ohms gives you 32 volts. Because I'm starting at 0, I better drop 32 to get to minus 32. And what's important here is that this is 2.67 amps. And so when I put it over here, 48-volt battery is contributing 2.67 amps up. The 54-volt battery is sending us 0.5 amps down. So we have, they are opposing. 2 batteries are indeed opposing. One tries to send 2.67 up, the other tries to send 0.5 down. The net result is 2.17 amps up. So this is 2.17 amps up. Combine that, you get 2.17 up. 2.17 times 12 ohm gives us 26 volts, and that's this way because current enters the plus. 0 volts, drop 26, minus 26 volts. See, now, once I'm done all this, we must forget about this. Very important to split up your paper. This is all gone. The useful piece of information is this, 2.17 amps, 26 volts, drop 26, we're at minus 26. This is minus 48, and we can solve the circuit then. So this drop must be dropping from minus 26 to minus 48, we drop 22 volts. 4 volts to minus 26. Can anybody tell me the drop across R1?
80.
How much?
80.
80 volts. 80 volts is dropped across R1. Amitaj, is your hand, you have another question? Is your hand up from before?
Sorry, sir, I forgot to lower the hand.
Oh, that's okay. 80 volts. We're starting here at 54 volts, and we're dropping all the way to minus 26 volts. So this is a drop of 80 volts. 80 volts dropped across the 24 ohm resistor. From 54 to minus 26. Some people prefer superposition. As I said, this one, I probably would have converted the voltage sources to current sources, or maybe done nodal analysis. Any questions? If you download the PowerPoint, you won't get my messy drawings, or you'll get the solution shown here, so you might want to practice this.
Okay, it's good for practice.
There is an error on this slide. I'm going to correct it. And anybody pick out the error that I made here that I have to fix? The error is in here. There is one error in here. One little error that I made. It would cost me quite a few marks in a test. I took 2.17 amps. I put it here. 2.17 amps. Heading up. Can you see the error I made? Yes, Flavio?
The current enter the plus and leave the minus. The resistor.
Yes, thank you. So the 26 volt is this way. 26 volts. So I did get this correct. This is indeed minus 26 volts, but it's minus 26 volts because we go from plus to minus. We electrically drop 26 when we start at 0. So I got the plus and the minus wrong. The minus and the plus. So this should be a plus, and this should be a minus right here. Current leaves the plus of a battery, and then it enters the plus and leaves the minus of volt drops. Unless the exception is if we are charging a battery, and that can happen if they're opposing and one's bigger than the other. Here, they are not opposing. Here they are aiding. No, I'm sorry, they're opposing, but one is not charging the other. They are opposing, but don't think we end up with a charging. This brings us to my very favorite. It's also the last one we're going to do. Extra. Hooray. The last one. And then we're done. Chapters 8 and 9. Thevenin's theorem says, no matter how complicated the circuit is, you could have 500 resistors and 20 power supplies and 5 current sources. You can replace it with a Thevenin equivalent circuit. How? Step 1, very important step. Step 1 says remove a portion of the network which will help you solve it. Usually this will be called the load, RL, but not necessarily. It could be anything. It's something, you remove something that's bothering you. Maybe you see series, parallel, and then a resistor that's not series and not parallel. Remove it. Remove something that will make the circuit easier. Mark the terminals where you removed that circuit, that portion. That's very important. Calculate R Thevenin, which is the resistance seen by at the terminals where you removed something. And to measure R Thevenin, we must turn off all the power sources. That means the voltage sources must be replaced by short circuits, and any current sources are replaced by open circuits. Same as superposition. Then we find R Thevenin. Then we determine E Thevenin by turning the power back on and measuring what voltage would appear at the terminals where RL used to be, that we removed it. And finally, we draw the equivalent Thevenin equivalent circuit. And the Thevenin equivalent circuit looks like this, where E Thevenin is our voltage source, R Thevenin is the resistor and the terminals. Very important, the terminals. A lot of people forget. Label them X, Y, A, B. Make sure you know the terminals. And then we put back in the resistor that was removed. RL, we reconnect it. And now we have a simple series circuit to solve. Very easy. 5 steps. Sometimes some people combine these into one, and then there's only 4 steps. Or some people say this is obvious, so there's only 3 steps, but those are the steps. 3 and 4 can be done out of order. Doesn't matter what order you do them. Let's try one. So we're asked to find the Thevenin resistance from the point of view of our load resistor. The thing about the load resistor is somebody here could be changing it all the time. So if we're changing that resistor all the time, I don't want to have to resolve this complicated circuit over and over. If I come up with a simple Thevenin circuit, it'll make life easier for me. So step 1 and 2, remove RL and identify the terminals. That's simple. We've just removed RL, and our terminals actually were already identified for us here, A and B. Sometimes they're not. That's step 1 and 2. Very easy step. We're left with a simple circuit, but we're going to make it even simpler. Step 3, R Thevenin. So you must look into the circuit with special glasses. You're looking in, what do you see? But when we measure our Thevenin, we have to make sure that our voltage source is turned off. When we turn off a battery, a voltage source at E, it becomes a short. And then you can see that the 3 and the 6 here are in parallel. Six and 3 in parallel give us 2 ohms. So now we have our Thevenin is 2 ohms. Step 3 done. For some people, this is a tricky step because you have to remember to turn off voltage source. It becomes a short. And then you end up with resistors that used to be, they used to be in series. But all of a sudden, they're in parallel. Depends on your point of view. Step 4, E Thevenin. We turn the power back on. So our battery is no longer a short, it's supplying 9 volts. And we're going to hook up our voltmeter to measure the voltage at terminals A and B. Now we note that terminal A and B actually is right across the 6 ohm resistor. So if we find the voltage across 6 ohm resistor, that will be E Thevenin. Well, what we have here is 9 volts divided by 3 plus 6. So that's 9 divided by 9. We have 1 amp. So there is 1 amp. 1 amp. 1 amp. When 1 amp flows through 6 ohms, that gives you a drop of 6 volts. So our Thevenin voltage is 6 volts. The Thevenin voltage is the voltage across these terminals here, 6 volts. Any questions about how we found E Thevenin? Okay.
Let me, the volt, because we use the voltage drop in R1, right? That's how we found E Thevenin.
We found E Thevenin. There's many ways we could have used voltage divider. We could have said E Thevenin. We had to properly determine that E Thevenin is VR2, which is VAB. That's E Thevenin. And that we could find as 9 volts multiplied by 6 over 6 plus 3. That's our voltage divider. And that would give us 6 volts. Or we could find I as 9 volts divided by our total, which is 9 volts divided by 3 plus 6, which is 9 volts divided by 9 ohms, giving us 1 amp. And then we can find E Thevenin. E Thevenin is VAB, which is VR2, which is 1 amp multiplied by R2, thus 1 amp multiplied by 6 ohms, giving us 6 volts. So whether we use voltage divider or we use just Ohm's law, we come up with 6 volts right here. And E Thevenin, which is VAB, is 6 volts, and that's what we extract from step 4. Step 5, draw the Thevenin equivalent circuit, which is just one battery, one Thevenin resistor, and then add RL back in. So in step 3, we found our Thevenin to be 2 ohms. In step 4, we found E Thevenin to be 6 ohms. This becomes our equivalent circuit, and we place the load back in the circuit. We now have a simpler circuit. If RL in the original circuit was 4 ohms, so if we make this 4 ohms, then I can find my I to be 6 divided by 6 ohms, that's 1 amp. Very easy to do. If somebody changes RL to 1 ohm, 2 plus 1, 3, 6 divided by 3, 2 amps. I can do this math very, very quickly. But if you were to say, I'm using 4 ohms, calculate again using 1 ohm with the original circuit, it's a bit more difficult. And this is an easy circuit. We still would have to look at 4 in parallel with 6 plus 3, and then do it again, 1 in parallel with 6 plus 3. This would take more time. So this is more difficult. And it's an easy one. Imagine if we had 2 or 3 voltage sources, a current source, 200 resistors, all in here. This would be very difficult if some cruel person were to keep changing the load. But if you come up with a Thevenin equivalent circuit, then change the load all you want. The math will be easy for me. So Thevenin is popular if you're going to make a lot of changes. Any questions? I'm trying to sell you Thevenin. trying to say use Thevenin. Yes, Amitaj.
So what if we have the number of, if here we have 3 and 6 are in the parallel, and if we have the 6, another 6 and another 4 and another 5 and then RL, and what we do to the simplify that, if we remove the RL, then there are 3 registers are in still are in the parallel, and when we find the E Thevenin, how will they go to in the series, or if we have to solve them into the parallel and then we can.
Yeah, so you're basically, with many words, saying, can we solve more complicated circuits? So hang on, I'm going to try and do that.
Okay.
We're going to do some more examples, and maybe that'll address your question.
Okay, thank you, sir.
This one was pretty easy. So Amitaj is saying, make it hard, make it more difficult. Okay. Well, this one's a bit more difficult. We don't want to scare you. Let's start with just a little bit more difficult. Example number 2, we've got a current source, some resistors, 3 resistors and a current source. Step 1 in Thevenin, remove R3. So the question would have said, find the Thevenin equivalent circuit with respect to R3, or maybe the question says, find the current through R3. If you're using Thevenin, start by removing it and identifying the terminals. That's really step 1 and 2. Remove R3, identify the terminals. Step 3, find R Thevenin. Now we got to be careful. It was not a voltage source, it was a current source. When we turn the power off to a current source, it becomes an open. And we're going to find R Thevenin looking in. Anybody want to hazard a guess? What's R Thevenin here? Looking in. You're looking in, or maybe to look in, you've got a multimeter and you're hooking up the meter here. And you're hooking up a meter here, and you're trying to figure out what is the resistance looking in. Well, the way these meters work, they inject the current at 0 open. So all the current flows through here. And the multimeter is using a 9-volt battery, and it sees how much current divides the two, and it gets the resistance. Well, current's flowing through 6 ohms. Can you see the 2 and the 6 in series? And we just end up with 6 ohms. Any questions? If your multimeter was using a 9-volt battery, then your multimeter, then the current here would be 9 volts divided by 6 ohms, or I think 1.5 amps, if that was the case. That's a lot. And but the net result, 2 plus 4 in series, 6 ohms. To find E Thevenin, step 4, we turn the power back on, and we have this circuit where 12 amps is coming from our current source, and How much of the 12 amps flows through the 2 ohm resistor? Can anybody tell me?
Zero.
0, thank you, 0 amps, because when we removed R3, we caused an open circuit here. And so the 0 amps, so that means all of the 12 amps must flow. All of the 12 amps must flow this way through the 4 ohm resistor. When 12 amps flows through 4 ohms, 12 times 4, we have a volt drop of 48 volts. That means 48 volts. 0, 48 volts. When 0 amps flows through a 2 ohm resistor, 0 amps flows through a 2 ohm resistor, we have 0 times 2, giving us a volt drop of 0 volts. No current, no volt drop. 48 volts, drop 0, 48 volts. B is connected to ground, so E Thevenin must be 48 volts. Any questions about how we found E Thevenin? Two pieces of information. R Thevenin, E Thevenin. Take those two pieces of information and we build our Thevenin equivalent circuit. Once it's built, we take R3 that had been removed and we put it back in, our 7 ohm resistor. But now we have a simpler circuit. And we can do all our calculations. We just have 6 in series with 7, that's 13 ohms, and we can find our current. 3.69 amps. So you might think, I could have solved this easier, maybe using current to voltage source conversion. Or maybe I can solve it just as is, or maybe I could have used nodal to solve it, sure. And maybe you have easier ways to solve it. But if somebody then says, I can't find any 7 ohm resistors, I'm going to change this to another value. Well, if you used any of these, you have to recalculate everything. If you use Thevenin, the recalculation is much easier if you make a change to that resistor. We're almost finished chapter 9, superposition and Thevenin. In summary, to use superposition and to use Thevenin, we must make sure that we know whenever we must temporarily turn off the power to measure resistance, or whether we want to temporarily remove a source, we make sure that we open current sources and we replace batteries with shorts. we'll need some practice. As Amitaj was saying, you know, maybe we'll, next class, I'll wait till, when's our next class? Friday. I'll wait till Friday to do a couple more complex circuits, because I think we've got enough right now. I am gonna leave my final sales pitch for Thevenin. Chapter 9 also talks about power. So power is important because maybe it's your TV or radio or stereo, you're playing music and you're connected to some speaker. Well, to be able to make the speaker as loud as possible, so we're sending power to the speaker. For maximum power, the speaker resistance must equal the resistance of, I was going to say stereo, yeah, speaker, stereo, iPod, whatever. They must be equal. And we're talking about the Thevenin resistance looking back in. If you are broadcasting to, I'm going to show it, an antenna, maybe even a dish, you want to broadcast radio, or you want to talk to the space station, you've got a ham radio and you want to talk. Again, the resistance must be equal. And we can simulate that. We can show that here. Whatever your system is, whether it's an iPod, an expensive Yamaha stereo, whether it's a ham radio that you're connected to an antenna or a satellite dish, and whatever this system is, it can be represented with a Thevenin equivalent circuit. And what you connect to it, whether it be a speaker, an antenna, a satellite dish or something, if its resistance equals our Thevenin, we get maximum power. So maximum power transfer is when RL equals our Thevenin. We could do a lot of math to prove that. So here we will not get maximum power. If we want maximum power, then we must change this to 9 ohms. If this is 9 ohms, we will get maximum power. If you have a stereo in your living room, big speakers, they're usually 8 ohms, and they match your stereo. Big stereo, lots of power. Being able to deliver lots of power usually means a small internal resistance, and they match. If you're listening with headphones to an iPod or a cell phone, these things cannot deliver a lot of power. We'll see later in later courses that means their resistance is higher, and here in this case, to deliver maximum power from something like an iPod, and you're listening with your headphones, then we'll see that it's probably more in the order of 2 kilo ohms. But your iPod here, its Thevenin resistance looking in is about 2 kilo ohms, and then we can get maximum power transferred to your iPods. So we must always look at matching. When you come in January, maybe we'll do this experiment, this lab. If you vary the load resistance here, as you start with, see, this is RL. If we start with RL being very low, like close to 0 ohms, we'll find that the power delivered is very low. And that's because, let's look at one of the formulas for power, I squared R. It's a series circuit, so we're going to have the same I, but I squared R, which is power, if R is 9 ohms, and over here, if R happens to be, let's use 0.1. 0.1 ohms, we can see that most of the power is going to go to the 9 ohm resistor. I squared times 9 is going to be much bigger than I squared times R. So very little power here. As we make R bigger, the power will go up. That's delivered here. So let's bring that all the way up to 9 ohms. When we bring this up to 9 ohms, I squared R, I squared times 9, I squared times 9. That's actually when we get maximum power. When we keep making R bigger, bring this up to, I don't know, 100 ohms. What's happening is that even though R is getting bigger, when we make R too big, I is getting smaller. So an interesting thing with power in a series circuit, as you make R bigger, you're making I smaller. So the total power, does it get more? Small? There's a square term. Square term means this is a curve. And when you plot it, you'll find the sweet spot right here where RL gets max power. That sweet spot occurs when RL and R Thevenin are equal. Any less or any more, we get less power delivered to the load. We'll try this out in class. You could try it with multisim if you want. You could build this circuit in multisim and prove it. Try varying RL and you'll see that we always get maximum power to the load when they are equal. And what's they? When the load and the Thevenin resistance is equal. So what do we need to know? Thevenin. Eber, where are you from?
I'm from Honduras.
Honduras. And the biggest city?
Is San Pedro Sula.
San Pedro?
Yes.
San Pedro. So if we want to deliver maximum power to San Pedro, to the city, then the Power Commission can try and make all the power lines and everything look like the same resistance. That might be an extension to an example, but the examples are endless as to when we want to deliver maximum power. It can be very large scale, or it can be as simple as hooking up my headphones, you know, to my cell phone. To get maximum power, we must match the resistances. This cell phone is not simply one battery and one resistor. There are thousands of resistors, transistors, diodes in here, but I can replace all of that with one Thevenin equivalent circuit. And in that Thevenin equivalent circuit is a very important resistor. And if my headphones match the Thevenin resistance, I will get maximum power to them.
Okay.
And that's it for chapter 9. Except for some more complicated examples, which I'm going to save until Friday. So I will see you all again tomorrow for computer interfacing at 11 o'clock, which is working on a project addressing any questions you may have. Friday, we'll carry on with practicing superposition and Thevenin a little bit more. We'll practice those on Friday as I do some examples. For the rest of this class, it's just any questions you might have here. Does anybody have any questions? I know you're recuperating from 1 or 2 tests here this morning. So the brain is getting full, maybe.
Yeah, it was in a rush.
Yeah. Okay, so we're going to stop here, and we'll carry on Friday with some more complicated circuits a little bit to try and solve them and get some practice in. Have a good rest of your day, guys, and I'll see you at 11 o'clock tomorrow for any 11 a.m. tomorrow morning for any questions you might have about computer interfacing project. Thank you.
See you, sir. Take care.